Hello everyone, welcome back. This is chapter 7.1 where we'll be discussing the use of fundamental trigonometric identities. And I just want us to recall what the fundamental trig identities are based on what we saw from chapter 6. Now there's a lot here to take in. In fact, we've seen all of this already. And there are some that are not listed here actually, like periodic identities, for instance, are missing. And maybe that's actually about it. But anyways, just to name a few, we have the reciprocal identities, we have the quotient identities, the Pythagorean identities, which are probably the most, maybe the most used, I think. Cofunction identities, which explains why the naming scheme is the way it is. Cosine is the cofunction of sine, and so on. And then the even odd identities. Okay. So now in this section, we're just going to be seeing the use of these and how we can basically simplify certain types of expressions. In the next section, we'll be verifying other identities. So we'll be given this identity and we can verify it using fundamental identities. So 7.1 really is like a stepping stone to 7.2. So to be honest, this section should be short. I've said that in the past, but I expect this video to be short. Anyways, let's move on and see our first set of examples. All right, so for these set of examples, well, they're all a little different. The first one should be not too bad because we've seen examples like this before. The second one is more of what I was talking about earlier, as for simplifying an expression involving trig functions using the fundamental identities. And this will be something like that, but it involves factoring as well. But let's first focus on the first one, of course. Now, it says secant of theta is equal to -3/2. So that right away knocks that one out. And we know that the reciprocal of cosine is secant, so that means this has to be -2/3, and that's using, of course, the reciprocal identities. And can we go a little further from here? Well, we also know the tangent is positive, so if you want, we could actually play the unit circle game and then go from, well, you know, in what quadrant is tangent positive, and what quadrant is secant negative. Since secant is the reciprocal of cosine, that means cosine is negative, and we can go from there. But there's actually a different way we can approach this. So instead what I want to do is I want to use a Pythagorean identity that involves either cosine or secant. I'll use the one that involves cosine. So the one that involves cosine is sine theta, well, sine squared theta plus cosine squared theta is equal to 1. Now we know what cosine is. Cosine is -2/3. So that means this is going to be -2/3 squared, which actually is 4/9. And we know it's positive because when you square a negative, you still get positive. And then that's sine squared theta. So if we subtract, 1 is 9/9 technically, if you want to get a common denominator. So 9 minus 4/9 would be 5/9, so that means sine would be plus or minus the square root of 5 over the square root of 9, which is radical 5/3. Now we don't know the sign yet though. And in fact, well, here's what I'm going to do. I'm not going to figure out what the sign is right away. I'm just going to keep it like that, and I'll fix this later. So we need to get back to this. Before we get there, though, well, yeah, we can find the reciprocal of that. But let's look at tangent. What do we know about tangent? Well, by the quotient identity, we know tangent is sine over cosine. Also, we are given that tangent is positive. So if tangent is positive, then sine can't be positive because positive over negative would be negative, not positive. Meaning, this actually has to be the negative one. Then we can reciprocate. When you reciprocate this, you get -3 over radical 5. But if you want to rationalize, you can multiply top and bottom by radical 5. So the denominator just becomes 5 itself, and you end up with this. Good. Now again, tangent is sine over cosine. So we know dividing fractions is multiplying the top by the reciprocal of the bottom. And we also know negative over negative will be positive. So this is going to be the top, which is sine, times the reciprocal of cosine, which is 3/2. And I'm ignoring the signs, of course, because I know the result will be positive. The 3's cancel, and we just get radical 5/2. And then reciprocating this, well, we'll get, let's see, it's 2 over radical 5. And again, if you want to, well, rationalize this, then you get 5 on the bottom, just like we did for cosecant. And there we go, that's our solution for the first example. Now moving on to the second example, the idea that we'll see here will kind of be more explored in the next one, but notice that they both have sine in common. So what we can actually do is we can factor out sine of x as a common factor. And when you do that, let me write it over here. We get sine of x outside of what? Well, we want to factor sine of x back in to get these two expressions. So that means this would lose a sine and just be cosine squared. And that makes sense because when you distribute sine of x into this and it multiplies to cosine squared, you indeed get this. But then sine times what will give you negative sine? Of course, it's just negative 1. So basically, you just lose a sign, but if you lose sine of x for both of them, for the second one, it's not 0, it's 1 when you divide by itself. So just keep that in mind. Now, this is kind of funny. This should remind us of this actual Pythagorean identity. Now, the reason why is because, even though it doesn't look like it exactly, it is actually just a different manipulation of this. In fact, if you subtract 1 to both sides, and then subtract sine squared to both sides, so I guess I'll have to justify it by writing it down. So let me write it below here. So I'm going to, there are a few ways we can actually do it, but I'm going to do this. I'm going to subtract 1 to this side, so that we get sine squared plus cosine squared minus 1 is equal to 0. So this is what we want, only with theta instead of x. So notice if you just subtract sine squared of theta to the other side, we'll actually get cosine squared minus 1 solved for. Meaning this has to be negative sine squared of x. Perfect. And now, sine to the 1 times sine to the second is just sine to the third. So in total, this is negative sine cubed x. Awesome. And I guess I should have boxed this whole thing too for the previous problem. All right, so now for this one, this is funny because to factor this, we can't really do what we did here because they don't all have the same thing in common. But there is a way we can manipulate cosecant in terms of cotangent, kind of, because there is actually a Pythagorean identity that has to do with cosecant and cotangent. And in fact, I've shown you before that if you had any one of the Pythagorean identities, let's just say the main one we look at mostly, and you wanted to convert it into one that involved certain themes, you can just get one of them involved. For instance, if we want cosecant squared involved, notice cosecant squared is 1 over sine squared, and here's 1, so if you divide everything by sine squared, like this, then you'll get one of those 3 Pythagorean identities. And in fact, what you'll notice is it will involve cosecant squared and also cotangent squared, coincidentally. So you'll get 1 plus cotangent squared in this case, that's theta, is equal to cosecant squared. Perfect. So we can replace cosecant squared outright with this, with 1 plus cotangent squared. Of x, though, not of theta, no. All right, so now if you rearrange things, you'll get this. You'll get cotangent of x, cotangent squared of x, actually, minus cotangent of x. These two combine to negative 2. Now, it doesn't look like it if you just look at it as is, but if you use a little bit of imagination, in fact, if you use substitution, it should become quite clear. So if you treat cotangent of x as a single variable, let's say, I don't know, u, then cotangent squared of x is just u squared. And u squared minus u minus 2 can actually be factored, and it factors as, well, let's take a look. Let me erase this. So if you think of u squared minus u minus 2, that actually factors as u minus 2 times u plus 1. Notice negative 2 and positive 1 multiply to negative 2 and add to negative 1 simultaneously. Good. And since u was cotangent, that means that this factors, now we've actually factored it, as cotangent of x minus 2 times cotangent of x plus 1. This will be actually extremely helpful in later sections where we will solve trigonometric equations. So imagine if this is equal to 0, we can actually factor this and set each one of them equal to 0, and then from there you can actually solve for cotangent in each of these cases using the zero product property, And then from there you can use inverse trig functions to actually solve for x. But that's a topic for another time. So to be quite honest, this is basically all 7.1 is. There are a few more interesting examples I want to see, and we'll just do 2 more. So let's take a look at those right now. So like I said, these are the last 2 examples, so let's just get right to it. Notice here there's t as our variable, and it may look kind of weird because the cotangent also has a t, but you know that's sometimes the variable we have to use. Anyways, let's see, how can we simplify this? The first thing that comes to mind, honestly, is just the quotient identity for a cotangent. Cotangent is cosine over sine, so we can actually write this as sine of t plus cosine of t over sine of t, and then times cosine of t. Now, of course, if you write cosine of t as cosine of t over 1, you can multiply these, so you'll get sine of t over 1 plus cosine squared of t over sine of t. Now, this is actually a pretty common idea when it comes to these types of simplifications. Basically, 1 is a fraction in disguise, so write it like that using a quotient identity or a reciprocal identity, and then combine the sum into one fraction with a common denominator, kind of like what we're going to do right now, multiplying this top and bottom by sine of t. Then, kind of following our nose a little bit, use any other identities that you see fit. In this case, I see the Pythagorean identity, sine squared plus cosine squared is 1, as long as the insides are the same. Of course, here they're both t. So this is 1 over sine of t. And what's 1 over sine of t? We can do better than that. 1 of sine over t, of course, is just cosecant of t. Which is actually pretty nice because it's a pretty simple looking result from a kind of complicated looking expression. And again, that's really what 7.1 really tries to drive home, is that you can get these weird, crazy long expressions involving trig functions, but then using some fundamental identities we saw in chapter 6, you can write it more compactly as a smaller, more simple expression actually. All right, so now moving on to this one. This is kind of similar to what I was just talking about, only they're already written as a fraction for us. In fact, they could have tricked us by writing this as cotangent, because notice cosine over sine is cotangent. But then it would be up to us to figure that out, that, oh, write it as a fraction and then combine common denominators. So I'm going to find a common denominator, and I'm going to multiply this top and bottom by that opposite denominator, sine, and this top and bottom by that opposite denominator, 1 plus cosine. And there's actually a visual way of doing this. It's known as a crisscross pattern when it comes to adding things with different fractions that have nothing in common. So basically we can multiply this by this by that, and then these to each other. But we're doing that anyways, it's just less visual, I guess. So we end up getting on the top is sine squared plus, if we distribute this, we get 1 plus, actually it's 1 times cosine, isn't it? So there we go. So it's cosine of theta plus cosine squared of theta over, well, I guess we could, I'm not going to distribute actually, I'll just leave it like this. 1 plus cosine of theta over sine of theta. And the reason why I'm not distributing is because I don't really see anything coming out from that distribution. Here, coming out from this distribution, and of course this multiplication, is sine squared plus cosine squared. So of course you could rearrange it if you want, but we know addition is commutative, so we can just write this as sine squared plus cosine, and again, what is sine squared plus cosine squared? You got it, it's 1. So altogether this is 1 plus cosine of theta over 1 plus cosine of theta times sine of theta. And look at that. Glad we didn't actually distribute this because they actually cancel out, and we're left with 1 over sine, and 1 over sine is actually coincidentally the same answer we got from the previous example. It is just cosecant. How funny. But in any event, that's really it for 7.1, and I'll see you in the next videos for 7.2. It's going to be fairly similar, but the types of questions are going to be a little different. So there's more logic involved there. Anyway, see you then. Thanks for watching.